Hello. I think we'll wait for a couple of minutes for students to join. Yeah, today's class is one of my favorite topics. So I work on binary analysis, like analyzing programs and analyzing binaries. And one of the things that I need to know, or like anybody who wants to do program analysis needs to know, is compilers. So we should have a very good understanding of how compilers work and how compilers generate the executable like from given source file, right? Uh, so yeah, in this class, I'll be going through like various stages of compilation and linking, and I'll show like with examples how like what happens to the C file when we give the C file to the compiler and what it produces. And once we get the executable, the a dot out, and what are the different ways in which operating system can provide memory for each executable and what each executable contains, right? I will be looking into that. So yeah, like does anybody like have worked with binaries? Like, have you ever looked into like elf headers, or like do you guys know object dump? Okay, I don't see any response, so I assume not many of you know like uh, yeah, okay. So, yeah, so yeah, linker scripts. Yeah, I think Thomas replied saying that he hates linker scripts. Yes, linker scripts are pretty annoying, and especially like, and they're very fragile, right? Like, if you had a single section, if the single section increases in size, you are kind of screwed because you have to now offset all the other sections. There are linker variables that you can use, but yeah, as you might have noticed, that it's just annoying. I agree. Uh, okay, I think we'll get started. So, as I mentioned in this lecture, we'll be looking into how the executable like a.out gets generated, and what does the executable says about the process layout. Basically, when the executable gets loaded by the operating system, where should it load? And how operating system, like what are the ways in which operating system can allocate space for a given executable? Okay, so I'll be using a.out and executable words interchangeably. So if you like when I mean a.out, that means I mean by program or executable. Okay. So let's start with the simple example. So here we have two files, main.c and math.c. So main has like two global variables, x and val, and it calls printf, scanf, and sign function. And the sign actually is in another file, which is math.c, and it has like three global variables, and it calculates sign and then returns the result. So what happens is when we give these two files to, for instance, GCC, so GCC first compiles these C files into object files, and then linker takes these object files and create a final executable, which is a.out. Okay. So and as we saw, main actually uses externally defined functions, that is sin, like sign or sin. Let's use sign. So sign and printf and scanf. Okay, so that means it calls certain functions which are not defined in the C file, in the corresponding C file. And how does program gets linked, and how does like main, like how does the compiler will make sure that the call in the main function actually invokes the sign function in math.c file? Okay, how does it happen? So the first stage is the compiler. So compiler just generates object file. So it takes the C file and it generates object file. And the object file, the information in the object file is incomplete because, as I mentioned before, so we could be referring to some functions which we don't have access to. We don't know where these functions, where the code of these functions is, right? So object files generated by compiler are kind of incomplete. And the main components of object file, there are many segments, but for our discussion, let's say uh, object file contains two segments: code segment and data segment. Code segment is the section of memory which contains code, and data segment contains data like global variables. And there are also other segments. These are heap and stack, which are kind of maintained by operating system, because program cannot know how much memory it will be using beforehand. So the memory for stack and heap will be managed by the operating system. And there is also size and address of each segment, okay, in the object file. Now let's look at the object file that is generated by GCC. So let me share my desktop rather than my screen so that I can show, like I'll run these commands and then show. Okay, perfect. So you guys can see my terminal, right? Okay, so I hope you can see my terminal. Okay. Perfect. So we have two C files. We have main.c and mat.c. As we know, main.c contains two global variables, x and val, and similarly, math.c contains something. I just used some multiplication to compute sign. So now let's compile. So in order to GCC, when you give C file, it actually does both compilation and linking. So in order to tell GCC to do only compilation, so you need to pass -c command, -c option, then you say main.c and you main.o. Okay, perfect. So we got main.o. Okay, good. So object dump is a command to view the headers of the object file. Okay, so it has various options, but X is one option which just dumps the headers. So here it has various contents. Like let's look at each section, like each component by component. So the first part is sections. Okay, so as we saw, like as I mentioned before, each segment or section contains the load address, basically the address at which the segment begins. Surprisingly, in the object file of main, so we see that VMA stands for like virtual memory address, which is the load address. So here we see that address of both text and data segment is 0. If you look at all the other sections, everything looks to be 0. It's surprising, right? Like how can multiple sections load at the same memory address? So this is because the reason for this is compiler cannot know what is the final memory layout of the executable. So compiler just produced an object file. However, memory, in order to know the memory layout, that happens when during the, like when we actually create the complete executable, right? So compiler doesn't know. So it just it just uses 0 for all the segments, or starting address of all the segments. Okay. And then in the object file also contains symbol table. So symbol table contains all the symbols that are defined, that are available within this object file. Okay. Why we need this symbol, we'll look into that later. Basically, like symbols say what are the things that are in this object file. Okay. let's look at few examples. For instance, uh, let's look at this main, like the one symbol. Okay, so here the value G means it's a global symbol. By global symbol, I mean, so this symbol can be referenced by other object files. Okay, so that's why there is G. L stands for local symbol. That means this symbol is only visible within this object file. So here we have G, which stands for global symbol, and symbol F says that it's a function symbol. That means it's a function, and it is present in text segment, and it has this address. Okay. Is the font better now? Okay. So F stands for function. So it's a function symbol, and it is defined in text segment, and it has address. Since the segment starts at address zero, so it's an offset from address zero. Then the symbol name is main. Okay. So there are various other symbols that are present, which are local to the object file. So I think people are waiting in the waiting room. I think I allowed everyone. Okay, so perfect. So okay, so that's the main, like that's a symbol main. So there are other symbols. For instance, let's look at, for instance, the first symbol, right? The first symbol is a local symbol, and it's df. D stands for it's a debug symbol. So that means it is used by the debugger. Okay? It has nothing to do with the object file or linking, but it is a symbol that is used by the debugger. And it's saying it's a file symbol. A small f stands for file, and it's saying main.c. Basically, this says that the object file is generated from a file name called main.c. That's it. Okay, so there are various other symbols, but you can ignore them for our discussion. Okay, so that's the symbol table. So symbol table contains all the symbols that are defined within the given object file. Okay. So if you see, yeah, we have main.o. Similarly, if we look at math.o, you have you also have the same symbol. Since we defined sine function in math.o, we have the corresponding symbol. Okay, and it also has the debug symbol that says it's generated from math.c. Okay, so another thing compiler cannot know is it doesn't know if functions that are used in the object file are defined in other object files or not, right? And it also don't know where in the memory that these functions will be loaded, right? So what compiler does is it just uses basically dummy values at places where it doesn't know the details. For instance, like if we look at the code, like in the main.o, if we look at the code of main.o, so there are many, like I hope you guys are comfortable with x86. But anyway, so the things that we need to understand is compiler doesn't know the address of, for instance, scanf, right? So it doesn't know whether scanf is even external function or some function that we define later in another object file. So in order to so what compiler does, it just replaces the call instruction with dummy instruction. So that's why if you see, all the call instructions almost have the same opcode. Like they all have the same opcode. For instance, this is the call to scanf. Here it's the opcode is E8000, which is same, and which is same compared with other call instruction. Again, every call instruction is almost dummy. right? Because it doesn't know what to put there, because it cannot put anything there, because the values of the functions depend on the memory layout of the executable, right? So it just places dummy values here. Okay. And then we should so we should have a way, like compiler should have a way to tell linker to fix this, because linker is the only one that can know all the entire scope of the executable, right? So compiler should have a way to tell linker uh, that these are the locations that linker should put the address of corresponding functions, right? So this is when this is to facilitate this, we have another piece of information called relocation information in each object file. Okay. So, and basically this says relocation information is a hint for linker, so that linker can use this relocation information and modify the values to the correct values. And the object file also contains other information that is for debugger that we have seen, like debug symbols, for instance. So like if we look at main.c, it has various symbols, like it has like global variables, xval, and it calls external functions. So the relocation information for main.c, like main.o, has like, so it says that there are relocation symbols for both global variables and function calls. So for each entry which linker has to modify, there will be an entry in the relocation record. There will be an entry in the relocation table where each entry is called relocation record. Okay. So printf is used twice. If you see in the main, printf is used twice. That's why there are two records for printf. So what this means is linker, when it figures out the address of printf, it should go to these two locations in the corresponding in the object file and replace the value with the correct address of printf. Similarly, when it finds if it finds, when linker finds the address of scanf, it should go to this location in the object file and then replace with the appropriate address. And finally, we also have global variables also have relocation entries. So that means since compiler doesn't know the starting address of final data segment, so compiler tells to the linker that it should also change the values of the addresses of the global variables according to the final address of the data segment. So similarly for math.o, we have relocation entries. Since math doesn't use any external functions, it just uses two global variables, right? So the relocation entries contains only for those two global variables. Okay, Thomas asked the question, are these principles the same for different architectures? Mostly yes, but these could be, the names would be different. For instance, like for ARM, this may not be true. Like instead of the type would be ARM 32, PC 32, okay? But the principles are same. The names would be different, by the way. Okay, oh, PLT stands for procedure linkage table. So that's when we will be looking into that later. So PLT stands for procedure linkage table. So type field, okay, type field is the type of relocation. So here the type field says PC32, it's relative to program control, and it is saying that it is in data segment. Okay, so it's type of relocation. So whether it is a relocation for the data or relocation for the function, and whether it is PC relative or not. So what I mean by PC relative is when you want to access some data, so you can access data in various ways, either using program counter or using absolute address. So, but PC relative means you will use your current program counter and use an index into the index. You basically add some offset to program counter and access the data. Okay. So if you don't understand the the type field completely, it's okay. So, but PC stands for PC relative. So what compiler does is it produces a nice object file which contains symbol table, data segment, code segment, and relocation records. Okay. Similarly, mat.c, we get we get corresponding object file. And so now when we give this object file to the linker, so linker actually has three functionalities, right? So first it needs to collect all the object files that are given to it, and it needs to figure out all the information that is present in all the object files. And it needs to figure out the final memory layout of the executable that it is about to generate. And it should combine all the segments from different object files. And finally, once it figures out the final segments, it needs to touch up. Basically, it needs to fix all the relocation records. And the result is the nice executable that we get. So, and note that linker can shuffle segments around. So that means linker can take, like, even if we give two object files, like in some sequence. So, but linker can take segments from like last object file, and it can put it before the first object files. So the segments can be shuffled in the final executable. However, within the segment, the functions will not be shuffled, for instance. Okay. So most of the linkers needs at least two passes, but in reality, linker, like real world linker, takes more than two passes, at least 3 to 4 passes. Okay. So in pass one, linker reads all the information from all the object files. It figures out what should be the layout of the final object file, final executable. And in pass two, that is when it actually writes the information into the new executable. Okay. In pass one, it's the processing pass. It figures out what it should do. And pass two is when it will do the things that it figured out in pass one. And in pass two, it also does, it also fixes up the relocation entries that we saw before. So yeah, pass one is just like processing pass, and pass two, it's address translation pass. And also this is also in this pass is when linker actually creates the new executable, or like a new object file. By the way, executable file is also an object file. So, and yeah, this is a summary of linker. So what linker does is, yeah, now given math.o and main.o, it combines the same segments from different object files into a bigger segment in the final executable. Okay. And then it will fix these entries. For instance, call 0, we saw that compiler puts like these dummy entries. So linker actually fixes them with appropriate function, with appropriate addresses. Okay. And also linker generates a table called procedure linkage table, which contains the functions that are not defined in the executable. Okay. So we know that main.o called main called like printf and scanf. So so these functions are not in the set of all the object files. So it creates the procedure linkage table to indicate to say that these are the functions that are not present, and the operating system or the loader should take care of linking them. Okay. So question is, does the linker create dependency graph to manage all the dependencies? Yes. How does OS load base address of GOT using global pointer? I mean PLT instead of GOT. So the interplay between PLT and GOT is tricky. So GOT provides another level of indirection. So we can go into the details of GOT later, because I mean that's a whole another section, a whole another discussion of interaction between PLT and GOT. For other students, if GOT stands for Global Offset Table, so it's a table that is present in the executable, which contains the offset of different global sections. Okay. So if you see the a.out, the code of main in the a.out, it's all fixed. So previously we had zeros here, right? So now it's all fixed. Linker nicely placed correct addresses in the main function, like in the main function, in the code that is generated for the main function. Linker did the fixing. And then the PLT, which basically contains the external functions that are called by the executable. So they are put into PLT section, which here it contains the name of the functions that is called by the executable. Like we call printf and scanf, so there are two entries. So if we called like different functions, we would have those entries as well in the PLT. Okay. And then once we actually generate this thing, when we actually execute, there is dynamic linking happens. So what dynamic linking means? So when we call function like printf is not defined in the executable, right? So dynamic linker actually loads the library from the system path, and it actually transfers the control to that particular code in the library. Okay. And dynamic linker and dynamic loader are like one and the same. The boundary between them is almost blurred. So dynamic loading is the process in which dynamic linker loads the binary, loads the library into the memory of the process. Okay. And then dynamic linker and dynamic linking and loading is all done transparent to the process. Process doesn't know what's happening. So if let's look at like how dynamic linking works in practice. Okay. So we generated object files. We generated 2 object files. So now we can use GCC to generate our executable. Okay, we got our executable. And let's look at, okay, let's see the code. First, let's look at the code of main to see if it indeed fixed. Oh yeah, I think, yes. It did fixed up all the entries, right? So printf, all calls are all fixed. Compare this with, so here we have, like, you see it's all dummy, whereas in the final executable, so we get the real, like the actual address. Okay. So once we get the executable, then dynamic linking happens when you run it. So in order to see how dynamic linking works, so there is a flag for the linker called, like, dynamic loader called ld debug. So this is an environment variable which will be passed directly to the loader. Okay. So you can set this environment variable, and then when you execute this, you get to see all the things that's happening that are taken by all the actions that are taken by the dynamic loader. So here you can see it first did some bunch of stuff. Okay. Like from the point that we started, dynamic loader actually loaded this Linux VDSO. This is for system calls, and this is wrapper for system calls. You can ignore all these things. It does a lot of setup. Okay. So after the initial setup, when we actually call printf, okay, once after the initial setup, it actually transfers controls to our executable, which is the entry point of the executable, which is main. So here, when we actually call printf, that's when DLSO, I think it's, there is a symbol lookup here. Okay. Do you guys see? I don't see printf. Do you guys see printf here? It should actually look for printf, right? Mm, debug all. Wow. Okay. So what it's doing is it's trying to find, okay, here, this is the call. This is the call inside dynamic linker. It's trying to look up the symbol for printf. It first looks into a dot out. It is not present. So it goes to libc. And when it finds the symbol in libc, then it actually binds, basically it maps libc into process address space, and it transfers the control to the printf function of libc. So dynamic linker, as you see, like it looks through all the system libraries that are present. And when it finds the symbol, it will actually transfer the control and the process executes. So now we saw like how a.out gets generated from given C files. Now, when we give a.out to the loader, there are various ways in which operating system can manage the memory that is needed for the executable. Okay, question is, when it finds the symbol, does it override the address the calling site is calling? No. What it does is it actually overwrites the address in the procedure linkage table. Okay, so in the procedure linkage table, for instance, the sim value is 000, right? So that means the address this is not resolved. So once actually dynamic linker loads and figures out the address of printf, it actually updates the value here. That's it. So it doesn't change the code. So next time when printf gets called, like it comes here, it sees the value to be non-zero, so automatically printf gets called. So the short answer is no, it doesn't overwrite the code, but it does overwrite the PLT entry. So dynamic function calls actually say call the function one. Yep, that's right. So now when we give executable to the operating system has to load the memory that is needed by the a.out. There are various ways in which operating system can allocate memory needed for the executable. Okay, so let's start with like very simple setup. Okay, let's consider our uniprocessor systems, the good old single process machines where the operating system runs one process at a time. Okay, so yeah, given a.out, operating system needs to load different segments into process address space. Okay, and yeah, and operating system also needs to take care of dynamic memory, like stack, heap, so on and so forth. So in case of simple uni-programming model, like where we have only one process running at a time in the operating system. So generally what happens is operating system, like we have physical memory, that's RAM, and you have operating system located at higher address, like at higher range of memory. And then program, now let's assume that program has single segment. So all the code, data, and everything is a single segment, okay? So this is like very old, like the initial systems. So there is single segment per program or like per process. So, and the program always starts at address 0 because there is only one process that is running in the operating system. So any given program gets always loaded at address 0. So process always starts from address 0. So here, it's very simple. There is no concept of virtual address. Like virtual address is the same as physical address. And this is actually used in early systems. Like the first machines that were created actually used this model because it's very simple, right? And like, what are the pros and cons? Like, of course, we are less efficient in terms of usage. And another thing is compiler now has more control of the address, because compiler now knows exactly the load address of the program, because load address is 0, right? So compiler can generate the final executable, and the operating system has to do very less work. It just needs to load, and boom, that's it. So yeah, and when we look, like, the code would look like this. So there will be a call with, and the calls will be absolute calls. That means, like, the address will be absolute address, and there is no translation, like there is no virtual address, physical address translation, nothing of that sort. And when there is a call instruction, the call actually jumps to this particular address, like the physical address, and it goes. And the compiler view is actually same as the operating system view of the, like, process address space. And in case of multi-programming, where we want several processes to coexist in the main memory, here there are many issues to achieve that, right? So first, we need to be transparent. That means process or the programmer should not care about where the process gets loaded, right? So it should be transparent to the processes. So irrespective of where we load the program, process should run. Okay? And there should be safety, in the sense we should make sure that processes don't corrupt each other. And then finally, irrespective of how well we are using the memory, we should also be efficient in using the CPU as well. That means we should not be doing unnecessary work in managing multiple processes. Rather, we should be efficient. Okay. So in case of simple, like very simple static memory allocation for multi-programming, here the idea is simple. So we have the highest memory that holds the operating system, and the other part of memory holds various processes, more than one processes. But this will not work. But the executable that we generated before, like the simplest executable, will not work, right? Because we are using absolute addresses here. So if you load this, our segment, at an address other than 0, good luck, it will not work, because we are trying to call address 0x30, but that address might be different, because the whole segment is offsetted or like loaded at different address. So this the old technique will not work. So how operating system handles it is the same, like the same principle as linker. Basically, a compiler now actually says to the operating system the places where operating system should do relocation, like the same thing that linker does. So which actually looks like this. So compiler now generates from 0, assuming that it gets loaded at 0. However, it also gives some information to the operating system that places where operating system should change. So when the program gets loaded at, let's say, address n or like address x, then operating system actually goes through the code, like the loaded code of the process of the program, and then it actually changes the address by adding the corresponding offset. Okay. And then everything works fine, right? Because we now change the address to the correct address, then everything works fine. So yeah, in case of multi-programming, different processes might stay in the memory at the same time. One disadvantage is that these are statically relocated. That means once a program gets loaded at some address X, it cannot be moved around. So it has to stay there until the program finishes. So, and this leads to inefficient use of memory, right? There is this fragmentation that could happen because the total available memory could be more, like we could have memory available, but it's in different holes. So we may not be able to use these holes in an efficient way. So ideally, in order to load segment 4, I should be able to move segment 2 to somewhere near the operating system, and I'll get enough space, and I can load segment 4. But that is not possible because there is no dynamic relocation. There is only static relocation. That means the rewriting of addresses that we saw happens only once. That is when the program gets loaded. Okay. So yeah, this is very simple, and however, it has various drawbacks. There is no protection. We wanted protection, but there is no protection because each process can like uh, like use like access or modify other process memory, and there is low utilization because of the holes, and there is no sharing. Imagine if each program loads its own copy of libc. Good luck. So libc is like 2 MB, like 2 megabytes. So if every process loads the entire libc, it's just inefficient, right? And then another thing is we want to in case of multi-programming and also uni-programming models that we saw, we are loading the entire contents, like all the contents of the program, into the memory, which is not needed. Why? Because like we don't, like, imagine Chrome. Let's say the size of Chrome is 10 megabytes. So when you execute Chrome will not be using all the code at once. Okay, Chrome might use some parts of the code for some time, and it might, and then it can go to another part of the code. So there is no need to load all the contents of Chrome into the memory at once. However, in case of simple program, like simple multi-programming and uni-programming models that we saw, entire program has to be loaded. So in the like next week, we will actually delve into more fancier things that operating system can do at runtime. Okay, so basically we'll be looking at the virtual memory, page tables, and very nice techniques called like uh, TLB, all the good stuff. Okay, any questions? Okay, guys, I think, okay, yes, okay. So yes, I will disable the waiting room. Yeah, I'll disable the waiting room. Yeah. Thank you, Ragul. Yeah. Yeah, I'm sorry for that. Like, anyways, this will be recorded. So for students who have missed the initial part, you can view the recording offline. But yes, I will disable the waiting room for future classes. Okay, that's it. Yeah, please start lab 3 early because, yeah, as you might have noticed from lab 2, things might get a bit tricky. Okay. Okay. Thank you.